Today we are going to look into capacitors. What is a capacitor? Capacitor is basically an electrical device which stores electric charge. Usually, not always, it consists of two parallel plates which could be filled with air or some dielectric media. And which can be usually charged with the help of a battery. So this is what in brief a capacitor is. The capacitor need not be a parallel plate. It could be of any shape. It could be a cylindrical, cylinder in a cylinder. We will connect this with positive. Or it could be even spherical. This could be one terminal. Any shape. But usually they are parallel types. Now, as we have seen earlier, if you take a very large sheet, which is having charge Q, then the electric field on both the sides are same, and it is given as charge by epsilon naught, where this charge is charge density per unit area, which is in this case, if the Q charge is appearing on this face of it, then the charge density would be Q by A epsilon naught. Sorry, since this is 2 in both the sides, it will be 2. Now, this formula holds irrespective of whether this sheet is conducting or non-conducting. But what we have to remember is the face. This Q charge is on this face of it. I mean, if I magnify the thickness of the sheet, Q charge is on this face of it. We are not talking about any charge on this face. If the charge is Q on this face, then only E in this direction or this direction, which is same, is given as Q by, this actually is the charge density to epsilon naught. Now we take some relationships regarding capacitor. Capacitor is defined as, this is the basic definition of a capacitor, is the amount of charge that it can hold for unit increase in voltage. This is the definition of a capacitor. Okay. Now, as we mentioned again before, in a capacitor, let's say parallel plate capacitor, the in-between media can be air or any other dielectric. Dielectric means some sort of a insulating material, like glass, ebony, etc. Now there's a term called K is the this is the dielectric constant. Higher the value of K, high K means more insulating. Okay, so let's try to drive the formula for capacitance. We have seen E is equal to epsilon naught by rho by epsilon naught, 2 epsilon naught. This is when we take any parallel plates, any plate, the media is air. For media air, we have epsilon naught. If the media is not air, then we have to replace it with actual epsilon. And what is the relationship between epsilon and epsilon naught? The relationship is K is equal to epsilon by epsilon naught. So if we still wants to represent electric field in terms of epsilon naught, then if the media is not air, then we take actual epsilon, and then if we still want to write it in terms of epsilon naught, then this will be 2 times K epsilon naught. This is our E. Now, if we take this parallel plate conductor, we have found out the value of E, and what will be the voltage difference between the two? We know that voltage is equal to E dot dr integral. Since E is constant, so we can take E outside, and dr and E are perpendicular to each other, or sorry, are parallel to each other. We are taking radius position vector in this direction, so is E. So this becomes, if D is the separation between the plates, then this becomes E times D. All right. So by definition, capacitor is Q by V. V we have got it here. What we can write is Q by ED. And what was E? E was epsilon. We take it from here. E is epsilon divided by 2K epsilon naught into T. Yeah. Now, we have seen this E. This E is on account of, if I say plate A, this E is, let us say that, make a fresh diagram. You have plus charge here, you have negative charge here. Because of this plate, let us say plate A, plate B, electrical field because of plate A will be epsilon naught sigma by to epsilon naught, which will be in this direction. If we take a point here, this direction will be this and EA will be this. Now what will be at the same point, what will be the field because of B? Because of B will be in the opposite direction. Sorry, field of B, because it is negative, this is again in this direction. So this is also same amount. And since both are in same direction, what we got is total E is equal to sigma 2 plus, this becomes our sigma epsilon. So instead of 2 epsilon naught, we will have only sigma here because of this relationship, because field is acted upon by both the plates. This field E is on account of plate A, which is in this direction, because positives from positive, and because of B, it is, since it is negative, so it is toward itself. Both are in the same direction, so they get it right up. So our E becomes twice of this value, which is sigma over K epsilon naught. Now, so if we substitute the value of Q by ED, that Q is sigma by epsilon naught. And what is our Q? Q is nothing but sigma A at A sigma naught by D. This is in case media in between was air. C is equal to A epsilon naught by D in case of air as a media. If we have any dielectric media other than air, then this becomes because then sigma will get, okay, let me write it again. If there is media other than air, then C is equal to A sigma D. And if I replace sigma by again epsilon naught, epsilon naught, this is epsilon naught, A K epsilon naught by D. So if we write a generic formula, the generic formula is C is equal to Ka epsilon naught over D. Now, if it happens to be air, then K is 1. That's simple. Just to reiterate once again, capacitance is defined as Ka epsilon naught by A, where K is the dielectric constant, A is the area of the plate, permissivity of free space, B is the separation between plates. Now let's try to calculate what is the energy stored in a capacitor. we know if two plates got a potential difference of V, the amount of energy which will be required to move a charge of Q across this will be how much? Q times V, right? Now, this voltage is V and additional charge is dQ. So dW is equal to V times dQ. And if we want to find total work done, then this will be dQ integrating over total Q. It may go from Q1 to Q2. This is equal to what? What is voltage equal to? We know capacitor is equal to Q by V. So V is equal to Q by C. So we can replace Q, V by this value. So our integral becomes Q by C dQ. So our this will be, yeah. And we can put back value of Q. Q is CV. So work done is half CV square. This is same as energy stored in a capacitor, which is charged to voltage V. Now, next thing we take is a system of capacitors. Capacitors can be joined in parallel and series. Now, when we join capacitor in parallel, what happens is one phase is connected commonly, second plate is connected commonly, and they ultimately connected to a battery. Now, if the capacity of one capacitor is C1, this is C2, C3, then the resulting capacity is C1 plus C2 plus C3. This is capacitors in parallel. Now the other way they can be combined is in series. We have C1, C2, C3. Like this. This is called capacitors in series. Now capacitors in series, the equivalent capacity will be given by 1 over C is 1 over C1 plus 1 over C2 plus 1 over C3 and so on and so forth. So if we take the case of a resistor, it is the reverse case. This is the case in case of resistor, this formula holds good for parallel, but in case of capacitor, this holds good for capacitors in series. Now, next thing we talk about is earthing of capacitors. Let's take a system of parallel plates. This may have a charge Q1, Q2, Q3, Q4, Q5, Q6. They are already pre-charged like this, and the charges are like this. Then, in a system of parallel conducting plates, the rule is the outermost surfaces shall have equal charge. In this case, the outermost surfaces are this. In this case, Q1 has to be equal to Q6. This is the condition. Now, we take another case. This is one plate, this is second plate, this is third plate. Again, Q1, Q2, so on and so forth, Q5, Q6. If we earth let us see, this was Q3, Q4. If we earth any of these plates like this is the configuration before we flip the switch. The switch is open and the charges are Q1, Q2 on this plate, Q3, Q4 on this plate, and 5 and 6 on this plate. Now, as soon as we close this switch, what will happen is the charges on these plates will redistribute. And they will redistribute in a fashion that now, earlier we had seen that Q1 should always be equal to Q2. But in this case, there's another condition that earlier Q1 was supposed to be equal to Q6. But now there's another condition when we earth it is that they are 0 as well. So this vanishes, and the charges will redistribute. Here, total charge on the plates after earthing will not be equal to total charge before earthing. Why is it so? Because during earthing, the electrons may flow to the plate or they may flow to the earth, whichever way. So since there will be the charge, if charge goes from earth, if the electron goes from earth to plate or from plate to earth, the charge is conservation of charge doesn't hold anymore because there has been loss or addition of charge. But this will still hold good. The outermost surface of this system will be 0. Now, keeping this condition, we can calculate the redistribution of the charges on the plates.